All right, in this video, we're going to look at the dynamics of surface gravity waves. We're going to do it in a very simplified case. And so the first thing I want to do is list all the simplifications we're going to make before we start. And hopefully I get them all because there's quite a few of them, assumptions or approximations. And so I'm going to make a long list. The first one, I guess, so assumptions, or maybe just simplifications. The first one, I guess, is that we're going to neglect any surface tension. Remember, the surface gravity waves are displacement of the interface of the water between the atmosphere and the ocean. And so normally there's going to be some surface tension due to the physics of water molecules at the interface. We're going to neglect that. So neglect surface tension. So in practice, this means that we're going to have to consider waves that are long, sufficiently long, so at least tens of centimeters long, so that there is absolutely no effects left over of the surface tension. I mean, surface tension will become important on a scale of a few centimeters. Okay, so neglect surface tension. The other one is no y variations. So all the action is going to be in the x and t plane. Variations only. All right, so nothing varies in the y direction. We're going to do that for simplicity. Another one is that the flat bottom, ocean of constant depth, H. Another is the no vorticity. Flow has no vorticity. So not that there's lots of vorticity in the ocean, but the physics of gravity waves, they don't require vortical motions, and therefore we can simplify it by assuming that there is no vorticity at all in the flow. Another one is no friction. So any viscous stresses are going to be neglected. No Coriolis force, no Coriolis effect. So that means that the period of the wave, the period t, is going to be small compared to the period of a day, 1 over f, the angular frequency. This one, very important one, small amplitude waves. And we do this so that we can linearize the dynamical equations. Linearize the dynamical equation. In other words, every nonlinear term, we're just going to throw them out, assuming that they're small. The nonlinear terms go like the product of small quantities, which is smaller than the main effects, so we can neglect them. Finally, I don't know if it's finally, but another one is the flow is incompressible. Flow is incompressible. And constant density. All right, so 1, 2, 3, 4, 5, 6, 7, 8 assumptions. Believe it or not, we still have some physics left in this. Enough physics to describe surface gravity waves. All right, so the setup is like this. Gravity is, of course, important, pointing downwards. Z pointing upward. This is the equilibrium surface if the ocean was at rest with no waves. At Z equals 0. The waves are displacements of this, called H, x and t. In the interior, somewhere down here, I guess, we have the bottom. And at the bottom, we'll have a boundary condition that W is equal to 0 at Z equals minus H. Right? There can be no flow in and out of the solid boundary of the Earth. So the velocity has to go, the vertical component of the velocity has to go to 0 at the bottom. In the interior, The fluid is incompressible, and so the divergence div dot v is equal to 0, which means that du dx plus dw dz equals 0. We also have the momentum equations. So but first I should say something about the pressure. So the pressure of x, z, and t is going to be the atmospheric pressure, PA, plus a part of the pressure that balances the force of gravity, which is minus rho g z, plus p primed of x and t. And this bit here is what we call the dynamic pressure. So this part, you can think of this as the atmospheric pressure, the pressure that balances gravity, sort of like the hydrostatic pressure, and then another part, whatever's left over of the pressure, we'll call that p primed. And so using this p prime, we can now write the momentum equations, the linearized one. So the x momentum equation, rho times du dt, the momentum, the rate of change of momentum per unit volume is equal to minus dp prime dx, right? The other ones don't vary in the x direction, so they all cancel. And similarly for rho naught dw dt, the vertical component is minus dp primed dz. And in this case, the gravity is killed off by this term. When I do d by dz of this, I get rid of the pressure term, and I'm just left with the dp prime dt. All right, and then we have some boundary conditions at the surface. So the analog of W0 at the bottom is that W is dh dt at the surface. So at z equals 0, we have a boundary condition. At z equals 0, W is equal to dh dt. Right, so the vertical velocity is the rate of change of the position of the particles in the vertical direction, which is just dh dt. H is the position of the particles at the surface. We apply the boundary condition at z equals 0, not at z equals h, and that's consistent with the approximation that the amplitude of the waves is small. So if the waves are small, then the difference between h and 0 is negligible, and therefore we can approximate it that way. And finally, we have a dynamical boundary condition, which is that p primed, also at z equals 0, p primed is equal to rho g h. And that's the pressure at z equals 0, it's just rho g h. Because at the surface, z is equal to h, and so the pressure at the surface is really rho gh, but we're applying it at z equals 0. So we'll have this boundary condition also. Okay, so these are our equations. The first thing we're going to do is we're going to derive a simple equation for the pressure alone, the dynamic pressure. And I'm going to do this by taking the time derivative of this equation, the divergence, the incompressibility equation, and I'm going to take the time derivative of this and eliminate du dt and dw dt. So if I do that, I do d by dt of div v equals 0, then what I get is d2u dt dx plus d2w dt dz, and then du dt is just dp dx, so this is equal to 0. du dt is just dp dx. Well, I guess I can multiply by rho naught, right? Rho naught to make it even simpler. And so what I have, if I substitute now, I have rho naught du dt, which is dp dx, or minus dp dx. So what I get is minus d2p primed dx squared minus d2p primed dz squared equals 0. I can multiply through by minus 1, and this becomes plus. So what I have is that the Laplacian in this xz plane of the dynamic pressure is 0. So that's one equation that I can use. This equation has to satisfy the boundary conditions, which are that at the surface, at z equals 0, p primed is equal to rho g z, subject to p primed is equal to rho g h at z equals 0. And at the bottom, I want w to be 0 for all time. So that means that dw dt has to be 0 for all time, right? If w is 0 at one time, but the rate of change of w is not 0, then at a later time, there'll be a flow through the bottom. So that means that dw dt is 0 at the bottom, which means that dp dz is 0 at the bottom. So I also have dp primed dz equals 0 at z equals minus h. Okay, so let's apply these boundary conditions, solve for p prime, apply these boundary conditions, and then apply the surface boundary condition. Okay, one thing I didn't point out last time is that the wave speed c is equal to omega over k, where omega is the angular frequency and k is the wave number. I mean, I did point this out, but the wave speed in general is going to depend on k. So typically you get some relationship relating the angular frequency to the wave numbers. So as you change the wave number, the frequency of the wave changes. And similarly, if you change the wave number, the phase speed changes also. That relationship between omega and k is called the dispersion relationship. And so one of the things we're going to try to get out of this mathematics we're doing now is what is the relationship between the angular frequency and the wave number? Or what's the relationship between wave speed and wave length? We're going to get this out of this mathematical analysis we're doing now. And so, so what's left to do is to solve this equation subject to these boundary conditions and then apply the surface boundary condition, which is w is dh dt. And once we satisfy all these conditions, we should get a relationship between omega and k. Now, that means we should look for solutions that have omega and k built into them. And we're going to look for solutions in the form of waves that are sines and cosines. But one thing that we have to, I want to backtrack a little bit, is that dealing with sines and cosine is a pain, because whenever you take a derivative of a sine, you get a cosine, derivative of cosine, you get a minus sign. And so when we're doing the derivatives of these waves plugging into these equations, the cosines and sines are always going to get mixed up, and it's going to be painful to deal with the mathematics of this. So it turns out that there's an algebraic way to deal with cosines and sines that is greatly simplifies the mathematics of this. And fundamentally, this boils down to the translation symmetry of the problem. If I move around in the x direction, then if I change the origin, none of the physics will change, right? It doesn't depend where I decide to call x equals 0. There's nothing magical about that. I just picked the coordinate system, but I could move the origin to be someplace else and I get the same physics. Same thing with the time coordinate, right? What I call t equals 0 is purely arbitrary, and there's a time translation that I could change the origin of the time without changing the physics of the problem. And so what I want is I want to get solutions which are invariant under this translation of time or space. Not the z direction, because that one's not invariant, but x or time or t. And what we want is we want to get something that looks like a multiplication when we shift. If we shift t, shift the origin, then we should want to get our same solution back but multiplied by some factor. Same thing if we shift the origin in the x direction to a different place, we want to get back the same solution but multiplied by a factor. All right, so that's all a little bit abstract, but what it boils down to is that what we need to do is go to the complex plane or the complex numbers in order to make these the mathematics much more simple. So it would think you're a complex number, this could be complicated, but actually it greatly simplifies things. So let me do a little aside on these complex numbers. All right. So this here is an aside on complex numbers. All right, so a complex number, z, is really composed of two numbers, a real part x plus what we call an imaginary part y. So I here, where I is equal to the square root of -1. And it's useful to view this geometrically in what is called a complex plane. So if I plot a plane here with y equals to the imaginary part of z plotted along this axis, and x equals to the real part of z plotted around this axis, then every complex number corresponds to some point in this complex plane. So if I put the point over here with coordinates x and y, then this is the same as the point z is equal to x plus iy. And the distance from the origin to that point, r, is the square root of x squared plus y squared over here. And if I define an angle theta, then this distance over here is just r sine of theta, and that's equal to y. And this distance over here, r cos theta, is equal to x. All right, so nothing special now, just that this is the imaginary axis. Now, the reason the complex numbers are nice is now I can express this complex number, z, in what are called in polar coordinates, in this way. So z is equal to x plus iy is equal to r e to the I theta, right? Well, why is that? Well, because the reason is that if I shift theta, if I multiply z by some complex number, another number, and I write it this way, then it's the same as multiplying the magnitudes and adding the angles to theta. So if I was to increment theta by a certain amount, right, by phi, for example, then this point here would be the same thing as r e to the I theta plus phi, if it has the same radius. Because now this distance over here, right, this is x is equal to r cos theta plus phi, and this one, this distance here, is r sine theta plus phi, because this angle now is theta plus phi. And so the nice thing is that this, now if I just multiply the new number, z prime is equal to e to the I phi times r e to the I theta is equal to r e to the I theta plus phi. And so that greatly simplifies the math, because now when I'm going to do my wave, I'm going to, instead of writing cos kx minus omega t plus sine kx minus omega t, I'm going to write it as e to the I kx minus omega t. And then if I increase t, it's the same thing as multiplying by a complex number, a phase number. All right, so it still seems a little bit abstract, I admit, but maybe when we plug in the solution, you'll see the advantage of this approach. All right. So let's look for a solution. Remember, we're trying to solve this equation, d2p primed dx squared plus d2p primed dz squared equals 0, subject to dp primed dz equals 0 at z equals minus h at the bottom. The pressure gradient has to go to 0 at the bottom so that W will remain 0 for all time at the bottom. And we'll worry about the surface boundary conditions later. All right, and then we're going to look for a solution of this form. P primed of x, z, and t is going to be some function of z, which I need to determine, times a wave form, e to the I k x minus omega t. Where omega is the angular frequency and k is the wave number. And you'll see now why this is a useful form of this of the solution. Remember, this is going to break down, well, I guess the solution is going to be the real part of this. P primed of x, z, and t is going to be the real part of this quantity. So I went to the complex plane, complex numbers, but in the end, the solution has to be real. So I'm only going to keep the real part of the solution. So there's this function of z which I need to determine, and I'll need to determine what k is and omega, how k and omega are related to each other. If I substitute this into this equation, then I take 2x derivatives of p prime, and each time I take an x derivative, it's like multiplying by ik, right? The derivative of the exponential is the exponential, doesn't change. So I get ik multiplied by itself twice for the x derivative. That gives me a minus k squared. So p prime d2 dx squared is equal to minus k squared f of z e to the I kx minus omega t. All right, so 2x derivative multiplied by minus k squared. So that was easy. Now 2z derivatives, well, d2 p primed dz squared, that's going to be equal to f double prime of z e to the I kx minus omega t. And if I add these two together and set it equal to 0, these e to the I kx's will cancel, and what I'm left with is minus k squared f of z plus f double primed of z equals 0. So this is a differential equation for f, second order, and the solutions are going to be just simple exponentials. So that means that f of z is equal to a e to the kz plus b e to the minus kz. You can verify that that is the solution, right? If I take a f primed of z, I get k a e to the kz minus kb e to the minus kz. That's the first derivative. If I take another derivative, f double primed of z, I get k squared a e to the kz plus k squared b e to the minus kz. And that minus k squared f of z, right, this is just equal to k squared f of z. And so you can see that f double prime minus k squared f of z is 0, and therefore this does indeed satisfy the equation. Okay, now I can apply the boundary condition to this thing. So I know that at the bottom, dp prime dz is 0. I already had f prime and I just deleted it. So dp prime dz at z equals 0, that's equal to k a e to the kz minus k b e to the minus kz. No, not at z equals 0, at z equals minus h. Has to be 0. So now if I replace z by minus h plus h, that is equal to 0. All right, so that's the bottom boundary condition, that w has to be 0 for all time. So this means that I can solve for a in terms of b, the k's cancel. So, b in terms of a. b is equal to a e to the minus 2kh, like that. So I just solve for b in terms of a from this equation. Okay, and then that means now I have the form of the dynamic pressure. There'll still be one arbitrary constant left, A. So let's me write out what the dynamic pressure is so far. I can get rid of this equation. And what I have is P prime of x, z, and t is equal to a e to the kz plus, and b is equal to a e to the minus 2kh. So plus e to the minus k z plus 2h times e to the I kx minus omega t. Okay, so now I have the dynamic pressure. I need to now apply the surface boundary condition. So what have I done so far? I have satisfied the continuity equation, satisfied the bottom boundary condition. I have a wave solution, but I have not yet applied the surface boundary condition. And so this is where the gravity will become important. So let's apply the surface boundary condition. So the surface boundary condition is that P primed of x, 0, and t should be equal to rho naught g times h of x and t. So this condition at the surface, if I plug in z equals 0, then that will give me h at the surface. So therefore h of x and t is equal to a over rho naught g 1 plus e to the minus 2kh e to the I kx minus omega t. This is of course at z equals 0, right? And so I plugged in z equals 0 here, I got that, and this gives me h. Now I had a kinematic boundary condition at the surface, and that was that w is equal to dh dt. So w at x, z equals 0, and t is equal to dh dt. And that's going to be equal to, if I do a time derivative of this, all I do is I multiply by minus I omega. So what I get is minus I omega a over rho naught g 1 plus e to the minus 2kh e to the I kx minus omega t. So that's the kinematic boundary condition that dh dt is w. Now I could go to the dynamical equation, the dynamic condition that dw dt is minus 1 over rho dp dz. So the dynamic boundary condition that dw dt equals minus 1 over rho dp dz. Right, this condition at z equals 0. What does this give me? Well, dw dt is like taking another time derivative of this thing, which will multiply another minus I omega t, which will give me a minus omega squared. So this side will be minus omega squared a over rho naught g 1 plus e to the minus 2kh e to the I k x minus omega t. All right, that's dw dt. On the other side, I get minus 1 over rho naught, minus, times dp dz evaluated at z equals 0. So dp dz, I get that from over here, and then after I take the z derivative, I substitute z equals 0. So that's going to be a times k 1 minus, right? If I take a z derivative, I'll get a minus k e to the minus 2kh. And because I'm plugging in z equals 0 after that, times e to the I kx minus omega t. All right, so this is this expression. That's the dynamic surface boundary condition. All right, so we have some simplification. One of them is that the densities cancel. The amplitude A cancel, that arbitrary constant. So A is an arbitrary constant, which is going to be like the amplitude of the wave. The condition for the linearity is that the amplitude be small, but as long as it's small, that the waves are not very steep, then it doesn't matter what the wave amplitude is. This is going to be a solution for any wave amplitude, provided it's small. All right, so the amplitudes cancel. This wave part, this complex exponential, this cancels. And so all I'm left with is the remaining terms, which I will write up here. And what that will give me will be a relationship between omega and k, which is the dispersion relationship we're after. All right. So what do we have? We have omega squared, I guess the minus is canceled too, is equal to g times k times 1 minus e to the minus 2kh divided by 1 plus e to the minus 2kh And that's everything, right? So this quantity here, that could be simplified further using what are called hyperbolic functions. So maybe you know this, but maybe you forgot. Hyperbolic cosine of x is just e to the x minus e to the minus x over 2. Hyperbolic sine of x is e to the x minus, sorry, got this wrong. Cosine is with a plus, the sine is with a minus over 2. And the hyperbolic tangent of x is e to the x minus e to the minus x over e to the x plus e to the minus x. Or, if I divide top and bottom by e to the x, 1 minus e to the minus 2x over 1 plus e to the minus 2x. And I divide the top and bottom by e to the x, I get e to the minus 2x, e to the minus 2x, and 1, 1. And that's what I have over here. So this is the same thing as gk hyperbolic tangent of kh. And so the dispersion relation, which is that relationship between k and omega, is the following. Use the red marker. Dispersion relationship for surface gravity waves. Waves is omega is equal to the square root of gk tangent, hyperbolic tangent of kh. We can look at various, so what it tells us, if I want to look at the phase speed, is that the phase speed is going to be a function of the wave number. So if I have very long waves, k is going to be very small. And so it'll be like dividing by a small number, so the waves will be very fast. On the other hand, if the waves are very short, then k is going to be a very big number. And well, I guess I should write down what c is. C is equal to omega over k is equal to the square root of g over k tangent of kh. So as k gets very big for small wave numbers, as k get very big for very short wavelengths, lots of waves per unit length, k is going to be very big. If k is very big, hyperbolic tangent, that approaches 1 in the limit of k very big, so I'm left with g over k. If k is a small number, the waves are going to get slower and slower and slower. So tangent of kh goes to 1 as kh goes to infinity. At the other limit, if I have very long waves, then tangent of kh goes to kh as kh approaches 0. So the hyperbolic tangent looks something like this. So this is +1, this is -1. And so in the limit of very big kh, this approaches 1. And in the limit of very small kh, it just looks just like a straight line. And it's just proportional to just kh. And so for the very long waves, kh goes to 0, and the dispersion relationship is c is just equal to square root of g times h. Right? Tangent kh becomes just kh, the k's cancel out of gh for c. So for the very long waves, the speed approaches a constant and therefore doesn't depend on the wavelength. So the very long waves, as long as they're sufficiently long compared to the depth of the ocean, then they don't disperse anymore. Right? And on the other hand, if they're very short, then they tend to 0 at very short wavelengths. K is very big, and so what we're left with is just g over k. And as k goes to infinity, very short waves, this goes to 0. So you would think that at very short wavelengths, the waves don't propagate at all. But there's some new physics that kick in at very small wavelengths, and that's the surface tension. So we cannot go to the limit of k going to infinity, because at some point your wavelengths are so short that surface tension is going to stop them from rippling, and then you should take into account the physics of surface tension, which is going to give them a finite speed even at the very short wavelengths. All right, so this is the dispersion relation. This is what we want to get for surface gravity waves. We have a relation between omega and k. We also have the functional form of the solution, which was that p prime expression from which we can get u and w that satisfy the boundary conditions. All right, so that's all I have for this analytical part. I think the next step is to go and plot some of these solutions on the computer, but we're going to do more than that. We're going to try to solve the same equations numerically using finite differences. So we can see another way of thinking about these equations and the physics of these gravity waves dynamically. And so before I leave you, I want to take, I know it's getting a long video, I want to show you the mesh I'm going to use to solve the equations on the computer. All right, so this is the finite difference mesh here. I just want to show it on the board before I show it on the computer, because it's a little bit easier to see it. So what we're going to have is a C surface over here, and the bottom down here, and this is z equals minus h, and z equal to 0, and we're going to divide the ocean into finite boxes. So this will be, let me just do a few here. So this would be z equals minus delta z, z equals minus 2 delta z, and all the way down to the bottom. And then over here, we're going to have x equals 0, x equal delta x, x equals 2 delta x, and so on. So the C surface is over here, and so we're going to define at the center of all the boxes, at the C surface, we're going to have a point, a mesh point, and we're going to define W there. And here also W. And here also W, and so on. And we're going to do the same thing over here. We're going to have a W. So we're going to define W only at these finite mesh points. And over here, and over here, and so on. All the way down to here, and so we'll have a W down here, and this one is just W equals 0. That'll be the boundary condition, W, and so on. We're going to define the U velocities, not at the same plate sorry, the U component of the velocity. We're going to define that on a staggered mesh over here. So U, 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 and so on. U, U, and U. And so this over here is at minus delta Z over 2. So all the U's are defined half a grid point down into the interior of the ocean. This one at 3 delta Z over 2, 5 delta Z over 2, all the way down to the bottom. And the pressure points, we're going to define them in the middle of all the cells. P. I guess these are P prime, the dynamic pressures, and so on. And the reason we do that is because now, when we want to do the acceleration in the x direction, we need a dp dx for the pressure force. We can just do a finite difference. To get the pressure gradient at the point U, we can just take the pressure at this point minus the pressure at this point, divide by delta x, and we get a good estimate, finite difference for the pressure gradient at this point. Same thing here, take the difference of this minus that, we get the pressure gradient. Conversely, in the vertical, it works out nicely also. If we want to get the acceleration for W here, that depends on the pressure force in the z direction, which is a dp dz, so we can take the pressure here minus here, divide by delta z, and we get the pressure gradient here. So pairwise differences in the vertical will give us the pressure gradients in the z direction. Pairwise differences in the x direction will give us the pressure gradient in the x direction. The only little tricky bit left is that when we get to the surface, we want to apply the boundary condition. We need a pressure gradient at the surface and at the bottom. If we can't do a pairwise difference, so what we're going to do is we're going to create a ghost point out here for the pressure. And over here, these are called ghost points, and we're going to define the pressure. They're really in the atmosphere, but what we're going to do is we're going to choose these so that we can satisfy the dynamic boundary condition at the surface. And similar down here, we're going to have a ghost point with the pressure down here. Pressure. And these ones are going to be chosen so that the pressure gradient is 0 at the bottom, so we can satisfy the kinematic boundary condition at the bottom. Okay, so that's all I wanted to tell you about the grid. We're going to see this again on the computer, but I thought it'd be nicer to see it on the whiteboard. All right, see you at the computer.